Hi, this is Gordon Parker from Michigan Tech, and in this video I'm going to review some basic circuit concepts. We're just going to look at resistors, inductors, and capacitors. And let's go ahead and say that we have a voltage drop across the resistor, a voltage drop across the inductor, and a voltage drop across the capacitor, VR, VL, VC respectively. And the current flowing through the resistor is IR, through the inductor is IL, and through the capacitor IC. And the resistor has value R ohms, the inductor L henries, and the capacitor C farads. So now all we have to do is write down some relationships between voltage and currents. So VR is equal to I times R. That's the easy one. And VL, the voltage drop across the inductor, is equal to L DIL dt. And the voltage drop across the capacitor is 1 over C, integral of IC dt. Now for the inductor and the capacitor, we can manipulate these a little bit to get IL. Basically, integrate both sides and divide through by L. And we get the integral of VL dt. And for the current through the capacitor, we can differentiate both sides and multiply through by C, and we get that, C dVc dt. Now before we do a quick example, let's just look at what happens to these relationships in steady state. And what I mean by steady state is, let's say that you have some circuit, it has a voltage source or a current source or some types of inputs, and you turn on those inputs to constant levels and let all the time histories of the voltages and the currents across the various devices reach steady state, become constants. We call that steady state. So there's no currents changing, there's no voltages changing, and some very interesting things happen. For instance, for the inductor, and remember, everything I'm saying right now is only for steady state, but for any inductor that you have in the circuit, take a look at this term. If IL is not changing in time, then DIL dt is equal to 0, and so VL is equal to 0, only in steady state, which means that the inductor becomes a short circuit. So you can literally just replace any of the inductor symbols with a straight line piece of wire and analyze the resulting circuit. For the capacitor, we can play the same game. Take a look at this element, or this term. So if VC is not changing in time, then IC is equal to 0, again, only in steady state. And so the capacitor becomes a short circuit, or becomes an open circuit. That one's pretty easy to remember because the capacitor kind of looks like an open circuit. The symbol, that is. So in steady state, replace your capacitors with open circuits, break the circuit there, and wherever you have an inductor, just replace it by a wire and analyze the resulting resistive circuit and see if that matches up with your steady state predictions of your differential equations that describe the system. So now let's do the simplest example in the world for these types of devices. What we'll do is we'll say that we have a power supply or a voltage source, Vs, and it's connected to a resistor and a capacitor. And we'll denote this R, this C. We have a voltage drop across the resistor and a voltage drop across the capacitor. And the thing that we're interested in is the voltage across the capacitor. This is an RLC circuit, sometimes called a low-pass filter, and it's used in some applications to filter noisy signals, maybe a noisy sensor. Let's say Vs is, instead of some voltage source, let's say it's a sensor, and you want to reduce the noise in that sensor a little bit using an RLC circuit. So let's generate the differential equation that describes this system. If we use KVL, Kirchhoff's voltage law, we're just going to do a sum of the voltages about each element and set that equal to 0. So we have a voltage rise across this, our sensor or supply or source, whatever you want to call it. And then we have a voltage drop across the resistor, and that's IR. And then we have a voltage drop across the capacitor, and that's V0. And we set that equal to 0. Now we have an equation with an input and an output, but we also have this other variable in there, I, that we really need to relate back to V0 to make this equation useful. Now let's see, that I is this I. That's the current that's going through the resistor and it's going through the capacitor. And so that I is also equal to C dVc dt, but we're denoting this as V0, so dV0 dt. And if I plug that into here, I'll get Vs minus RC V0 dot minus V0 equals 0. Rearrange this just ever so slightly. And put a box around it. There's our differential equation that describes how the output voltage changes due to a change in the source voltage or the sensor voltage Vs. Now before we go on, let's just look at this a little bit more. Let's play this game where we check it by looking at it in steady state. So let's say I were to give Vs a step input. So it's cruising along here at 0, and then I give it a step at some point in time. And eventually, way out here, as time goes to infinity, the circuit reaches some steady state condition. So there's no more changes in voltages across the capacitor, no more changes in I, the current flowing through the circuit. When that happens, if I look at it strictly mathematically from this differential equation, my V0 dot term, this term, becomes 0. And so V0 is equal to Vs. Now if I look at it from a circuit standpoint, and I use the check from the previous page, what we would do is set the C, this thing, to an open circuit. Let me just switch colors and redraw this. I would have Vs plus and a minus, and that resistor, and that is my V0. So I would have the sum of Vs minus the voltage drop across the resistor, this thing right here. However, there's no current flowing through this because it's an open circuit. So there is no voltage drop across the resistor. So my V0 is just equal to Vs, which is exactly what we got from just looking at the differential equation and applying a steady state condition to it. Okay, so this doesn't prove that my differential equation is correct, but it does give me a way to check to see if I have any gross errors, and I don't. What else can we do with this? Let me switch to yet another color. How about blue? And we'll look at this differential equation just a wee bit more. Let's look at it from the standpoint of units. Okay, we have volts over here, volts. We have volts over here, and we have volts per second right here. From this little analysis, this tells me that RC, the units for RC, are seconds. Well, it turns out that this RC circuit, RC, has a very special name. We call it the time constant. And I'm running out of room, so I'll just write it up here. So RC is the time constant for that circuit. And it's a characteristic time that tells you how quickly or how slowly the circuit achieves some behavior. And we'll look at that in simulation. So if all you wanted to do was to get a quick review of R's, L's, and C elements and do a quick example, then you can stop right here. If you want to go a little bit farther into MATLAB Simulink analysis of this system, then stick with me. But before we do that, we're going to make one more examination of this differential equation. So we have RC V0 dot plus V0 equals Vs. What I'm going to do is put this into transfer function form. I'm going to take the Laplace transform of it and solve for the output over the input. That is V0 over Vs. So if I take the Laplace transform and letting the initial conditions be 0, I get this. I'm using capitals for Laplace domain quantities. And now I can solve for V0 over Vs. And I get 1 over RCS plus 1. Again, there's my time constant again. And we're going to play around with this transfer function in MATLAB and Simulink. Alright, so what I'll do is I'll define R, my resistance, as being 100,000 ohms. And my capacitance as being 1 microfarad. Now if I look at my time constant, R times C, I see that it's 0.1, and we know that the units of that are 0.1 seconds. Let's just create a quick transfer function of it. Numerator is equal to 1, and our denominator from the previous slide that I was annotating is R times C for the S field, like so. And we can whip up a quick step response of this in MATLAB using the step command. Boom, and there we have it. Let me blow it up just a little bit. And actually, let me throw a grid on it and bring it back into view. Okay, remember our time constant was 0.1. And here's our time history on the x-axis. We can see that when we hit it with a step input, it turns out the step command uses a input level of 1. So we gave it a step input of 1. And the response of the system has this exponential rise, like so, up to 1. At time equal infinity in steady state when nothing is changing, notice that V0, the output, which is what we're looking at here in blue, is equal to the input, which was equal to 1. So again, we have confirmation of our V0 equals Vs. Now here's our time constant, 0.1 seconds. If we go up to here, we'll see that at 0.1 seconds, the response is equal to about 0.63. And if I zoom in on that, I can get a little bit more confirmation on that. So at 0.1 seconds right here, we're at just about 0.63, 0.632. Another way to look at it is that we're at 63% of the final value that we ended up at. That's very important. We'll explore that a little bit further when we're getting into control system design. Now let's play around with this in Simulink for a minute. So let me fire up Simulink. And that takes just a moment to come up. And what we'll do in Simulink, instead of looking at the step response, because we already did that, let's look at it from the standpoint of a sine wave input. And what I'll do is I will go over to the continuous palette and grab a transfer function. And maybe I'll zoom in a little bit. How about that? And I'll just call this RC. Make this just a wee bit bigger. There we go. And what I'll do is I'll go to sources and grab a sine wave. Oops, that sinks. Go to sources, grab a sine wave, stick it in there, and what I want to do is look at how the response changes for different frequencies of the sine wave. And what I'll do more specifically is, let me copy this, and I'll make a couple versions of it. And I'll scoot these up just a little bit. Make one more, like so. And I'll go over here to signal routing and grab a bus creator. And this will just allow me to look at the signals with nice names on them in just a minute. We have 4 things. There's 1, 2, 3, and 4. And what I'll do here is, let's see, amplitude of 1, that's fine. Frequency in radians per second, let's make it 0.01. Actually, no, let's make it 0.1. And here we'll make this frequency 1 radian per second, that's the default. Here we'll make this 10 radians per second, so I'm just going up by factors of 10. And we'll make this one 100 radians per second. And finally, I'll go to sinks, and I'll put a scope on here. And now I'll name these things. So this is 0.1 radian per second, 1 radian per second, 10, and 100. Wonderful. And let me do one more thing. Just set up the simulation environment. We'll go to fixed step, RK4, and how about 1e to the negative 5th? Let's see, this looks about right. Oh, I didn't really want to save it. So let's just go ahead and simulate this. Oh, there probably is a couple adjustments I need to make to the scope. So let's go in here. By default, the way I have MATLAB set up is the scope is limiting us to the last few thousand points. So we'll go in here, this little gear symbol, history, and get rid of that limit. Go into general, click on legends, that way we can see all of our nice labels, and redo the simulation. Here's our labels. So now we can see what signal is which. And what did we put in here? Oh, hey, look at this. I didn't fix up the these. So I wanted this to be R times C, right? So let me get rid of this, this, and this. And I'll just copy these down here like so. And redo this. Whoa. Redo it like so. And there's the simulation running along. Now remember, the amplitude of all those sine waves is 1. Our lowest frequency sine wave is here in yellow, and we really can't even see a cycle of it. So maybe I should let this simulate for just a little bit longer. How about 25 seconds? There it goes. There's our yellow, which is our lowest frequency. That was 0.1 radians per second. And it gets right up to 1 amplitude of 1. Then it's going to start coming back down again. The purple was at 1 radian per second. And that still gets up to 1 also. Plus or minus 1. The 10 radians per second, though, which is actually 1 over our time constant, right? Our time constant was 0.1 seconds. And if we invert that, we get 10 radians per second. That's the cyan line. And its amplitude is a little bit lower than 1. So it's been attenuated. And let's just zoom in on that. Oops, not there. How about right there? And if we zoom on that some more, we get it's close to 0.707. Now that's an interesting number, right? 0.707 is 1 over the square root of 2. And then if we go to the highest frequency, 100 radians per second, that's 10 times faster than 1 over the time constant. That's the red line, and it's attenuated quite a bit. Right? And if we zoom in on that, we can see all the little oscillations, but it's down to 0.1 instead of 1. It's attenuated by a factor of 10. Turns out we could have predicted all of this from looking at the transfer function and doing a little bit of frequency domain analysis. And that's a topic covered later. But what we get out of this is that for high frequency signals, we've attenuated the source quite a bit. And for low frequency signals, they've basically been left alone. Now, remember what I said about the RLC circuit is that sometimes it's used to filter noisy signals, noisy sensors. Well, let's play with that. This is our last exploration of this very simple circuit. Let's play with that with a new simulation. And what I'll do is grab one of these, bring it over here, and let me zoom in a bit. And how about, I'm going to close this scope. And as a source, why don't we grab another sine wave? We're going to grab 2 sine waves this time. What I'll do is I'll make a sine wave that is our main signal that we're trying to work with, and I'll add some noise onto it. How about some 60 hertz noise? The kind of noise that you might pick up if you have a noisy 60 hertz environment. Okay. And before we actually feed it into this, let me grab another scope. I'll just grab the scope from here. And let's just take a peek at that signal. So let's give this an amplitude of 10. And the frequency is 1 radian per second. That's fine. And we'll leave all that alone. And now let's add our noise. So this is our noise, and this is our sensor. And we'll make the noise, let's see, well, 60 times 2 times pi. It's at 60 hertz. Now let's give it a little bit of phase shift for the fun of it. And we'll go to fixed time step again. And how about RK4? We'll go 1e negative 5th again. Whoops. And let's simulate that. Wow, that's some noisy business. So if I zoom in on this, let me blow it up a bit, and then zoom in. So here's our high frequency 60 hertz noise. Here's our low frequency signal. We'd really just like to get that signal out, not all the noise. So I'll break this, put this over here, and I'll bring this in like so. And how about we'll use under signal routing, a bus creator again, so that we can have some nice labels. And I'll call this one, bring that down there. How about we call this one filtered? And I'll call this one raw. And simulate away. So the yellow is our raw, and the purple is the filtered. we can see that through this RC circuit, we've attenuated this noise substantially. Now we do have a little bit of a phenomenon here. If you look at the peak of the yellow, it's right around in this region. 1.6 seconds, somewhere in there. Whereas the peak in the purple is a little bit shifted to the right. So there's a wee bit of phase shift associated with that signal. Now the amplitude was 10. Was it 10? Let's just double check that. The sensor amplitude was 1, and the noise amplitude was also 1, so quite a bit of noise. And so sure enough, our purple gets right up to 1. So it's not much of any attenuation in terms of the filtered signal. However, if the sensor signal was faster, let's say it was at 10 radians per second, and the noise we leave at 100 radians per second, here's what we get. Now we can see that instead of the purple getting up to 1, it's only getting up to that 0.707 point again. So we have quite a bit of attenuation. We actually have quite a bit of phase shift. Right, here's the peak in the yellow, and here's the peak in the purple. It shifted almost 1/10 of a second to the right. That's much more phase shift than we got at the lower frequencies. So the moral of this story is, if you want to filter something, you could use an RC circuit. You have to be a little bit careful how you do it. You also have to be careful of how you pick the R and the C, because you will get some magnitude attenuation and some phase shift. That might be okay if all you're doing is doing some data acquisition and desiring to look at that signal. Clean it up a little bit as you're viewing it. But if you're using it for closed loop control, then you have to be very careful about these two effects. And again, we'll get into the details of that in a later video. So in summary, we looked at RLC circuit elements and did a very simple example, but then took a very deep dive into that very simple example, that being the RC circuit. So thanks for watching. And again, this is Gordon Parker from Michigan Tech.